how to solve trigonometric equations that just have one trig function, and you're just kind of doing some algebra, then taking an inverse, and remembering that cosine is positive or negative, and sine is going to be whatever number you get, and then pi minus that. So equations like this, right? So you should be able to solve something like 2 sine theta minus 1 equals 0. Okay. What we're going to do today is I'll go through this one first just to kind of set a baseline. But today we're going to be looking at how to combine kind of all the things that you have learned in trigonometry so far in terms of trig identities and combining linear combinations of sine and cosines, and kind of harvesting all of these skills to solve equations that are a little bit more complex. So to solve this, right, I just say sine theta equals 1/2, and then I take an inverse. And if I want the full set of solutions, I'm going to get that theta equals 30 degrees plus 360 degrees n, or I could get theta equals 150 degrees plus 360 degrees n. Okay. And then, depending on what range I want, if I want the range of solutions between 0 and 360, then I could say, okay, that's going to be 30 degrees and 150 degrees. If I'm looking for solutions between, say, 180 degrees and 360 degrees, I'd say, oh, there just aren't any, right? And these are the general solutions for everything. So this is what you should already be able to do. We're going to look at solving something that gets, let's take it just a little bit trickier. So let's say I want to solve sine 2x cosine x plus cosine 2x sine x equals 1 for x between 0 and 2 pi. And remember that the square bracket means inclusive, so you'd be including 0, and the parenthesis curved not square bracket means you're excluding this range here, the 2 pi. Okay, so if I look at this and I want to solve this, this is where you say, hey, if I just try to do this by itself, there's no way I can solve this equation. But what I can do is I can say, oh, hey, this actually kind of looks like the sum, right? This I could write as sine 2x plus x, because I know of that identity, right? I can rewrite this whole side of the equation as one nice simple function, and this will be equal to 1. And then once we're here, now this is trivial to solve, right? I just have sine 3x equals 1, and then we'll get 3x equals pi over 2 plus 2 pi n, and then x is pi over 6 plus 2 pi over 3n. So that gives me that my solution set is going to be pi over 6, 5 pi over 6, and 3 pi over 2. Okay. So here, this was nice. We only needed kind of a single little transformation. You just recognize identities. These problems reward you for being very familiar with trigonometric identities. So try to kind of internalize those. As often as I say, I think memorization is not the most useful thing in math, because if you need something, you can look it up. The place where it does kind of come in, less memorization, but more familiarity, is if you're able to look at this equation and immediately recognize, oh, hey, this is that identity that we learned, then you're going to have a much easier time. And we'll see an example later where the difference between recognizing one and not is pretty substantial. So let's do one that's a little bit harder. Let's say this time I want to solve cosine 2 theta minus cosine 4 theta equals the square root of 3 sine 3 theta for theta contained between 0 degrees and 360 degrees. So this is wild, because this has 3 different arguments, right? So there's nothing that I can do here that's nice and easy. What you might see if you look at this for a little bit, or you're very comfortable with your identities, is that I can write this as the cosine of 3 theta minus theta. And I can write this as cosine of 3 theta plus theta. And once you see that, then all of a sudden the problem becomes doable, because now what I can do is I can expand these out accordingly. Right, so once I write this as cos 3 theta minus theta and cos 3 theta plus theta, I can use my sum and difference identities to expand. And when I do that, a bunch of stuff cancels out, and we end up with the double sine terms essentially adding together. So I'm going to get 2 sine 3 theta equals root 3 sine 3 theta. So once we're here, I usually ask students what they think the next step is, and there's always one who says, at least, it's very common to believe this, that we should divide both sides by sine 3 theta. Don't do this. Do not do this. It's a mistake that hopefully you should only make one time. If I had an equation like x squared equals x and asked you to solve this, you wouldn't divide both sides by x. You know that you're getting rid of a solution if you do that, right? Same thing here. If I divide both sides by sine 3 theta, I'm going to be eliminating one of the possible solutions, at least. So we're not going to divide by trig functions. Never, when you're solving general trigonometric equations, should you divide by a trigonometric function, okay? So instead what we're going to do is I'm going to bring this over. So I'm going to have 2 sine 3 theta sine theta, that's a bad sign, minus root 3 sine 3 theta equals 0. And then I'm going to factor out the sine 3 theta instead. So I have sine 3 theta, 2 sine theta, minus root 3 equals 0. And once you're here, you're going to use the zero product property. To remind you what that is, if I have a product that is equal to 0, then it means that either one of those things must be 0 in order for the statement to be true. So I could either say that sine 3 theta equals 0, or I could say that 2 sine theta minus root 3 equals 0. And then I'll rewrite this as sine theta equals root 3 over 2. So what we've done, typically when you solve trig equations in the past, you end up doing one inverse sine or inverse cosine, and that gives you 2 sets of solutions, since it can exist in 2 quadrants. But here, we've already split once, and then we're going to inverse these and split again. So we're actually going to end up with somewhere around 4 sets of solutions. And some of those, will be overlapping, and you could maybe rewrite them as fewer. But kind of baseline, you could have up to 4 sets of solutions. So if I do this, the inverse sine of 0, I'm going to have 0, and then I'll get my 2 sets of solutions. So I'll have either theta is equal to 0 degrees plus 120 degrees n, because I divide by 3. There's the 3 theta in there. Or I could have theta equals 60 degrees plus 120 degrees n, and that comes from the 180, and you divide by 3. And then over here, I have either theta equals 60 degrees plus 360 degrees n, or I get theta equals 120 degrees plus 360 degrees n. And now I have these 4 things, and yes, they do overlap, and you could simplify it if you would like, or we can just go through and pick out all the values that fall within the range we're looking for. So I'm going to have 0 degrees, 60 degrees, 120 degrees, 180 degrees, 240 degrees, and 300 degrees. Oops. 300 degrees. Right. And you can see this is just all the essentially, if you just rewrite these as 0 plus 60 degrees n, then you generate the full set, and that's what we're looking for. So we have 6 solutions here, 4 different equations. So solving general trigonometric equations can get a little bit more. You'll get more solutions sometimes than you would when you're solving some of the less involved trig equations where you don't need to use identities or anything like that to solve them. Let's look at another one. Let's say I have cosine squared theta plus sine theta plus 1 equals 0. And I want to solve this for theta between 90 degrees, or negative 90 degrees, sorry, and 270 degrees. Kind of a weird range, but whatever. So I'm going to rewrite this as 1 minus sine squared theta plus sine theta plus 1 equals 0. Then my 1's combine, and I'm going to have sine squared theta minus sine theta plus 2, or minus, oops, yeah, I'm also adding to the other side, so this is a minus 2, equals 0. I just like having my leading term be positive. And then once we're here, it's not super clear how we would do this, right? But this is where you want to kind of think back and think of sine theta as your variable. And think about if you had x squared minus x minus 2. And we can actually factor this. It's a quadratic equation, right? It's like a trigonometric quadratic equation. So I'm going to factor this and write it as sine theta minus 2 times sine theta plus 1. And then that's equal to 0. So now I can use the zero product property and say that either sine theta equals 2 or sine theta equals negative 1. This has no solutions, right? Sine never takes on values larger than 1. Sine theta equals negative 1 does work, though. We get theta equals 270 degrees plus 360 degrees n. So what I'm going to do is this is, excluded here, so I can't use 270, so I'm going to have to subtract 360 from it, and that gives me that theta is equal to negative 90 degrees. That's my full solution set there. Okay? So kind of another trick is if you end up with this quadratic structure, you can basically factor it like you used to with quadratic equations. All right, now let's go to kind of the trickiest problem here. So this is example 5. Suppose I give you sine theta divided by 1 plus cosine theta. And we say it's equal to 1, and I want you to solve it for theta between 0 degrees and 360 degrees. So this, there's nothing that jumps out at me as being able to simplify this. I'm going to show you 2 ways to do this. The first way is going to be, we'll call it method 1. Oops. So for the first one, what I'm going to do is I'm going to multiply both sides by 1 plus cosine theta in order to generate sine theta equals 1 plus cosine theta. Now, here's the thing. I just finished telling everyone never to divide by trigonometric equations or functions, because if you do that, you are eliminating solutions. So by multiplying by a trigonometric equation, what do you think is going to happen? If you said that you think we're going to introduce additional extraneous solutions, you are correct. I have multiplied by a trig function in order to solve this, which means that when I get to the end, I'm really going to have to check all the solutions that I get and plug them back into the original and make sure they work, because some of them might not. Okay? So from here, what can I do? Well, I'm actually going to square both sides. And again, by squaring both sides, that means I'm going to introduce more extraneous solutions. So we're really going to have to be very careful at the end about checking our answers. Okay, but now once we're here, this becomes a little bit nicer. I can rewrite this as 1 minus cosine squared theta equals all of this stuff to 1 plus 2 cos theta plus cosine squared theta. And then I can group stuff all on one side, and I'll get 2 cosine squared theta plus 2 cos theta equals 0, where my 1's cancel, then the cosine squared comes over here to be 2 cosine squared. My 2's I can just cancel out, right? So then I get cosine squared theta plus cosine theta equals 0 if I just divide everything by 2. And then I'm going to factor this, because remember, we do not divide by trig functions. So I'm going to factor this. I'm going to get cosine theta times cosine theta plus 1 equals 0. And this gives me 2 sets of two things that could work, right? Either cosine theta equals 0 or cosine theta equals negative 1. And when I do this, I get, for this side, either theta equals 90 degrees plus 360 degrees n, or I get theta equals 270 degrees plus 360 degrees n. This one only gives me one solution because it's -1. So I'm going to get theta equals 180 degrees plus 360 degrees n. Okay. So now what I do is I look and say, all right, what falls within the allowed solutions? And I have 90 degrees, I have 270 degrees, and I have 180 degrees. And now what I want you to do is go ahead, check these, plug each of these back into the original equation. If you do, you're going to find that these are extraneous. They do not work. They are not actual solutions to our original equation. They popped up because we multiplied by a trig function and then we squared trig functions. So our actual full solution set is just 90 degrees. Okay. Now, we did a ton of work here to get here. And then at the end, we had all these messy extra solutions, had to check them. That's a huge pain. So this is where you get very, very rewarded if you are quite familiar with trig identities. Because method 2, and you might say, oh no, we don't have enough space, but that's because method 2 is really easy. Method 2 is to recognize that sine theta over 1 plus cos theta is actually just tan of 1/2 theta. And if it's just tan of 1/2 theta equals 1, then that means that 1/2 theta equals 45 degrees plus 180 degrees n. You divide by 1/2, multiply by 2. Theta equals 90 degrees plus 360 degrees n. And theta, the full solution set, is equal to just 90 degrees. So in the corner, in the margins of my notes here, in 3 or 4 lines, we can get the solution and avoid all of this work just because we recognize that this is actually a half-angle identity of tangent. So anytime you can, let yourself do less work, you definitely should. They always say the best mathematician is a lazy one. If you can, find a clever way to solve a problem rather than just brute forcing it, then definitely do the clever way. You're going to save yourself a bunch of time and effort, and usually it provides more actual insight to the problem anyways. So that's solving general trig equations. Thanks for watching.